Okay, let's look at an example of a hypothesis test. Let's suppose that the average amount of lead in the blood of young children is 2 micrograms per deciliter. A city recently changed its water supply, and there have been reports of increased lead levels. A concerned doctor wants to look in the city's medical records and find out whether the kids in the city have blood levels above this average level. In a sample of 35 children, she found a mean lead level of 2.6 micrograms per deciliter with a standard deviation of 1.9 micrograms per deciliter. We want to perform an appropriate hypothesis test at the 95% confidence level. Okay, so let's set this up. So I like to set up my sample information first. So let's see, what do we have here? What's our sample size? 35. They have a sample mean of 2.6. And they have a sample standard deviation, remember that's a lowercase s, of 1.9 micrograms per deciliter. Okay. So then we want to figure out if our assumptions are met. So we need what? Either my n bigger than or equal to 30, or my variable normally distributed, whatever variable we're measuring, in this case the lead level, and if we reread our problem, I don't see anything about assuming that the lead levels are normally distributed, but do we meet the n bigger than or equal to 30? Yes, we sure do. Okay, because we have an n of 35. So that means my assumptions are met. Okay, so you always want to check this first. Now, at least in our class, we're not going to really learn what to do about it if they're not met. There are some other more sophisticated, different kind of statistical techniques that are more complicated that can sometimes be used. But for us, what we would do in our class is just say that the test is not appropriate for this. We do not meet the assumptions. So you do want to be able to check for that. And then what do we need next? We need our hypotheses that we're going to be testing. So our H0 and our H1 or our HA. Okay, so for this we need to figure out what benchmark we are comparing against. So what is our benchmark? Average level of 2 micrograms per deciliter. That seems to be our benchmark, right? So mu equals that. And so then what we need to decide for our alternative hypothesis is it a two-tailed or a one-tailed test? So what we want to do is we want to reread the problem and see if there's anything steering us in a particular direction, like they think it's going one way versus the other. So what do we need? The doctor wants to dig in the records to find out whether the kids have blood levels above the average. Okay, so this right here, this is what is going to tell me that I have a one-tailed test. Okay, so there's my clue. So that means I'm going to be setting this up as a one-tailed test. So that means my mu is bigger, because it says above, than my benchmark. This is a good place to also write down your alpha. So what's my alpha? My confidence level is 95%, so I subtract that from 1 as a decimal, so I end up with 0.05 for my alpha. Okay, so then I do my sketch. And I'm going to put, so what am I going to do with my sketch? Ooh, it's a one-tailed test. That means I'm only going to shade in one of the tails. So I'm only going to shade in this upper tail on the right side. Because we're assuming that it's likely impossible that the kid's lead levels are lower than that. So the whole alpha goes into this one tail. Okay, so the whole 0.05 goes over there. Okay, and then we need to write down our critical value, so right here, so this is going to be, and remember we don't know the population standard deviation, we only know the sample, so this is going to have to be a t-value, so this is going to be t.05, okay, and so we mark that on our picture. Okay, so far so good? Okay, so now let's keep going. So now the next thing we need to do is find the critical value. Okay, so to do my critical value, I am going to need my t-table. And what goes into the t-table, we need our degrees of freedom. So remember that is going to be n minus 1, and my n is 35, so that's going to be 34. And we also need our right tail area, which we can get from our picture. So we need the degrees of freedom, we need the right tail area, and then my critical value is going to be, let's go look it up. Okay, so we go to our t-table. So I scroll down to my t-table. Wait, it should show up. There it goes. Okay, and so right tail area, so that's the area represented by the numbers across the top of this table. And then the degrees of freedom are down the left side, so I'm looking for a right tail area of 0.05. Oops, hang on, that's not the right number of decimal places. 0.05, here it is. And degrees of freedom of 34. And so let's see where those intersect. So let's see. That is going to be 1, 2, 3, 4. This is actually easier if you have a paper table instead of this thing. So it's going to be this one, this 1.691, right? Let me double check. Yeah, 1.691. Okay. All right, so I'm going back. So 1.691, so then I'm going to go put that onto my picture right here. Okay. Okay. So now we need our test statistic. So I usually do this in two steps. My first step is to find the standard error. Okay, and so my standard error, remember, is the sigma of all the x bars. This is going to be approximately equal to the sample standard deviation divided by the square root of n. Okay, it would be exactly equal if we had the population standard deviation to stick in there, but we don't. Okay, so go to my sample information here in the upper left corner. 1.9. divided by the square root of 35. And so this should be approximately 0.3212. Okay? So then we need to actually do the test statistic. Okay, so our test statistic, the way we always calculate it, is we subtract what we are comparing, and then we divide by the standard error. So ours is going to be a t-value. So we're going to do x bar minus my benchmark divided by this standard error that we just calculated. Now when I do that standard error, I normally store it in a variable in my calculator, like I store it in variable A. And so then I can just use that in this calculation when I'm ready to put it in. So let's see, what's my x bar? My x bar is 2.60, and then what am I comparing it to? 2, right? So I'm going to do 2.60 minus 2 all over this 0.3212, and I didn't write the units here, but you can see they're both in the same unit, so it's going to cancel out numerator and denominator. And so then this gives me what? About 1.868. So then what I'm going to do, I go to my picture and I go look to see if that falls in the rejection region. 1.868, it sure does. So my 1.868 is going to be over here somewhere. Because it's bigger than 1.691. And so that means that we are going to reject our null hypothesis, right? So because that falls in the rejection region, we are going to reject H0. And so that tells me that this sample provides evidence that the kids in this town have average lead levels above that value of 2 micrograms per deciliter that is considered normal. So something may be going on with the water supply. Okay? So that is how we do that. Let's do another one. So let's suppose that a manufacturer claims on the package label that the package has 8 ounces of potato chips. So someone buys 50 bags of chips and weighs them and calculates the sample mean. And they get a sample mean of 7.89 ounces and a sample standard deviation of 0.2 ounces. And so what we want to know is whether this sample provides evidence that the labeled value of 8 ounces may be inaccurate. And we are asked to use alpha equals 0.1 level of significance, and we are told that we can assume that the package weights are normally distributed. Okay, so let's start writing down our stuff. Okay, so let's see. So my sample size is 50. My sample mean is 7.89 ounces, and my sample standard deviation, lowercase s, is 0.2 ounces. Okay? So here's where I like to check my assumptions. Okay, so what do we need? We need either my n to be at least 30 or variable to be normally distributed in the whole population. Okay, and so what do we have here? So let's see, is our sample size larger than or equal to 30? Yes. And is my variable normally distributed? Yeah, so this time I've got both of them, but you really just need one. So I'm just going to write that right here. Okay, so we met our assumptions. Okay, so that means we can proceed. So we're going to write down our hypotheses. So we need our null hypothesis and our alternative hypothesis, H1 or HA. By the way, you notice I don't usually use a dash for this. It's maybe a little obsessive on my part, but a dash looks like a minus sign, right? And we're not subtracting anything here, so I like to use a colon when I separate these. Okay, so I need my mu here, and so I want to figure out what's my benchmark. So what's my benchmark here? My benchmark is the 8 ounces that's labeled on the package, right? And so then we need to decide, is it a one-tailed test or a two-tailed test? Let's see. Is it steering us in a direction? Does the sample provide evidence that the manufacturer's labeling may be inaccurate? Inaccurate could go either way, right? So I don't see anything steering me in a direction here, so I'm going to call this a two-tailed test. So I'm going to draw a line through my equal sign. And I'm also going to write down my alpha. My alpha is 0.10. Okay, so now for the picture. Okay, so I look to see, do I have a one-tailed test or two-tailed test? I have a two-tailed test, so that means I'm going to shade both tails. And I'm going to put alpha over 2 in each tail, so I take my 0.10, I divide it by 2, and so that gives me 0.05. That goes in this tail. And then I also have alpha over 2 in this tail. Okay, and I mark my critical values where the color changes. So this is going to be T subscript 0.05, because that's my right tail area. And then this is the negative T 0.05. Okay, and we're using T because we don't have the population standard deviation. Okay, so that's our picture. All right, so next thing to do is to figure out my critical value. Okay, so for my critical value, I need a right tail area and I need the degrees of freedom. So my degrees of freedom, n minus 1. So that gives me 49. And then the right tail area is equal to 0.05. And so then my critical value is, well, let's go to our table and see what happens. Oh, okay, so there's our table. And so what we want to do is we want to find degrees of freedom equal, oh, I don't see a degrees of freedom equals 49. Okay, so this is going to depend on what table you have. You may not have the same table that I'm using here. So you may have it. If you do, you should use that value. If you don't, just use the closest value. If you're using tables, you can get more accurate if you use technology, if you use a calculator or a computer to generate the exact value with all the decimal places of your critical value. For most purposes, a lot of what we're doing here is approximating anyway, right? So if you're little bit off in the third decimal place, it's not usually that big a deal because you're not usually right close. If you're going to be right close to the edge of the critical value, you probably need to go find a way to dig it out of a computer and get as accurate as you can. But in most cases, that won't happen. So we're going to just go with the closest. So we're going to go with this 50 here, and we want a right tail area of 0.05, so that's going to be the fourth column in. So I'm going to come 1, 2, 3, 4. So that's going to give me this 1.676. So that's the one I'm going to use. And let me go back. Let me just write a note here, what I just told you. So my table doesn't have a degrees of freedom equals 49. So let's use the closest degrees of freedom that it has. And that's going to be a degrees of freedom of 50. So approximately, well, so T.05 is going to be about 1.676. So that's the number I got from the table. I guess I don't need that there. Okay. So I'm going to put that 1.676 on my picture. And then we have negative 1.676 over here. Okay, and so then now we need to figure out our test statistic. Okay, so first thing I want to do is my standard error. Okay, so this is supposed to represent the sigma, the standard deviation of all the x bars, but we can only approximate it. So I'm going to use s over the square root of n. And so my s is 0.2. I'm going back to my sample information, 0.2 ounces over the square root of 50. And you're not using the degrees of freedom here, you're using the square root of 50. And so this turns out to be approximately 0.0283, it looks like. Yeah, I'll just do that. Yeah. But I don't worry too much about how many decimal places I write down there because I will just save this in a variable in my calculator so that I can put it in when I do my test statistic. Okay, and so then that's next. Okay, and so for this, we are always going to subtract what we're comparing. So that's going to be, we're going to compare x bar to our benchmark value, and then we're going to divide by this standard error. And so when I actually work this out, so let's see, so my X bar was what, 7.89? So 7.89 minus my 8 ounces divided by, the 8 ounces is my benchmark. That came from my hypotheses right there, 8 ounces by my mu. And we're going to divide that by this 0.02828. I'll use the value I stored in my calculator. I'll retrieve that variable a where I stored it. And then this turns out to be about negative 3.89. Okay? So now we need to go look and see where that is on my picture. So where is negative 3.89? Well, gosh, it's way over here. Way over in the rejection region, right? Okay, so that's definitely a rejection. Okay? Okay, so since we ended up in the rejection region, so what do? We reject H0. And then that, to reframe that in terms of the problem, so we're going to say that this sample provides evidence that the average package size, or package weight, I guess, differs from the labeled value of 8 ounces. So it looks to me here that maybe they're not giving us enough potato chips, right? Okay, so that's how we do our hypothesis test. Okay, let's do a really similar example. In fact, if you don't read this carefully, you may think it's the same problem, but it's really not. So it's the same situation. So what's the difference between this one and the other one? We have a different sample size. So in our sample information, this time our n is only 10, right? Notice I put here the same mean, and I put the same standard deviation as before. Now this is unlikely in real life that if you did such a different sample size, you would get the same value. Even if you do the same sample size, you probably wouldn't get the same value. But I wanted to show you what happens if everything stays the same except for the sample size. Okay, so we should check to see if our assumptions are met. Okay, so what do we need? We need n bigger than or equal to 30. Which we don't have, or we also need the size to be normally distributed, which it is. So that's in the last sentence of our problem statement. So we got this one, right? So we got one. We only need one of them. I should put an or there. So we only need one or the other of these. So the answer to this is yes. So that means we can actually do this procedure. And I'm going to shortchange some of this stuff because, of course, we already did it, right? So we'll just go over what changed. So I will go ahead and write down our hypotheses. So those are the same. So we still have a mu equals 8 ounces for our null hypothesis, and for our alternative, we have still have a two-tailed test. And notice we're using the same alpha here of 0.10 as we used before. And so our picture is going to look the same. So let's see. So if I do my picture, we're going to do what? Okay, we're going to put half the alpha in each side. Okay, so alpha over 2, that's going to be what? 0.05. And then we're also going to have alpha over 2 over here, right? Okay. And so we've got our t's here. Okay, so a lot of that looks the same as what we did before, right? Okay, so now we need what? The critical value. Okay, so on our critical value, if we were using z's, it wouldn't matter, right? Because our sample size would not affect the z's. But with this, it does, because the sample size affects our degrees of freedom, right? Okay, so we need what? The degrees of freedom, that's going to be n minus 1. So this time we only have 10 bags of chips. So this means our degrees of freedom are only 9. So we definitely have a small sample here. So my right tail area is still the same. That part doesn't change. Okay, so now let's go to our table. Okay, so let me flip back over to my table. So degrees of freedom equals 9. So that's this one, 0.05, fourth column in. So this is going to be this 1.833, right? So that's a different value than we got before. So 1.833. Okay, so now we need to go get our test statistic. Again, the procedure is just like we did before, right? But the numbers are coming out different, aren't they? Okay, so we first need our standard error. Okay, and so my S over my square root of my N, and so this is going to be, my S is still the same, right? So 0.2, but my N is different. So this time I have the square root of 10 down here in my denominator. So let's see what that is. So that gives me about 0.06325, which I will store that in variable A in my calculator, and then I can use it in the test statistic calculation. Okay. So we're going to always subtract what we're comparing, divide by the standard error. Okay, and so then this time I still had 7.89 for my mean. I still had 8 for my benchmark. We're going to put this stored value in here. And so we end up with about negative 1.74, right? Okay. So now I want to go back to my picture. And so I want to figure out where to put that. Oh, and I didn't ever write my critical value in here, did I? Let me do that before I go any further. 1.833. So this should be on here already. So 1.833. And then this one is going to be negative 1.833. Okay, and so now we need what? Negative 1.74. So where is negative 1.74? Oh, okay, it's actually just a smidge to the white side of this. So it's going to be in here somewhere, right? So that is going to be my negative 1.74. So notice that my t value is not in the rejection region. Okay, so we're going to say here, we are not going to reject H0. And so we're going to say that this sample does not Okay, so it does not tell us that the average weight of the bags differs from the package value. Okay, so notice something. Everything stayed exactly the same except for the sample size. So these t-tests are highly dependent on sample size. So you have to be careful with that, because if you don't have a big enough sample, then you end up sort of not having what they call the power to reach a statistically significant conclusion. We call it statistically significant if there's a statistically significant difference if we do end up rejecting the null hypothesis. If you get a big enough sample, you can have it be really close to the 7.89 to the 8. If you have a big enough sample, you could end up rejecting the null hypothesis with an even closer value than that. So that's just kind of FYI, and you can learn more about that if you end up taking a more advanced statistics class somewhere in your future. So, but just keep in mind that the sample size makes a really big difference in these. So I hope this helps you understand hypothesis testing. Good luck, and I will see you next time.